Okay, so now we have enough information so that we can link all of this back up to prime and composite numbers and orders of operations. Right? Exactly how does this section fit in those specific topics? Right? So let's work. Right? Let's work with this idea. This is how I'm going to teach this topic. Right? Firstly, I'm going to teach you. I give you the logic first, and then I'm going to give you the exact title. So let's say we were given 2 to the power of 3 and we multiplied that by 8 squared. How would you simplify this? Right, the only way you could simplify this is by putting it in your calculator. There is no rule that I discussed thus far that will enable you to solve this otherwise. So the way we have to do this, because we are dealing with a product here, you have to use the product rule. Do you understand? Because we are dealing with a product, we have to use the product rule. And that's very important because there's something that we need to note, is that we have to ensure that the bases are the same. We have to ensure that the bases are the same. Now, remember when we discussed prime and composite numbers, this is why I'm linking it back to prime and composite numbers. When we had a number like 16, I said that there's two ways that we could break the number down. We could break it down as a product of prime numbers, or we could break it down as a product of prime and composite numbers. However, if I took this composite number and I tried to refine the number even more, this composite number will break down as a product of prime and composite numbers again. And eventually what's going to happen if I break this composite number down, we are going to have a product of only prime numbers. And this should look exactly the same. Do you understand? So this is why we say eventually if you try to express 16 in its most simplest form, that simplest form will be the product of prime numbers. Right? So save the trouble and just get straight to the point. Right? So and we also discussed that if you're trying to compare numbers, it's best to put them in the prime form because it's in the simplest form. So if you have two things in their simplest form, you are able to compare them. But if you have one thing that's in the simplest form and one thing that is complex, how are you able to compare them? Understood? Exactly. I gave that entire analogy about the human body and so on. So now to have these bases be the same, let's express all of these bases as prime bases. So it'll be 2 to the power 3 will remain the same. But 8 squared can be represented as the following. You see 8 can be represented as what? 2 cubed. So 2 cubed represents 8. We have to include the 2 on the outside. Right, so now we're using a couple of the rules that we're using the power to the power rule. So now if I have to simplify all of this, this will be 2 cubed multiplied by, when you're raising a term to a higher power, you're raising a power to a higher power, you multiply the power. So this will be 2 to the power 6. And whenever multiplying terms with the same base, what do? You add the indices. So this will be 2 to the power 9. This is what we call exponential expressions to prime bases. And now I hope at this point you should see the significance of prime numbers, because prime numbers help us to compare things, they help us to simplify things down, and now you can see how it's lending itself into the exponent section. If you haven't watched the video on prime numbers in detail, please watch it and ensure that you understand that idea fully, because we are not done with prime numbers. When we start discussing exponential equations, we are going to bring prime numbers back in, and you're going to see how everything links. Maths from this point forward is going to become very interesting. If you've been following all of my work, it's going to become very, very interesting. Now let's do another example. Let's say that we have 49. Let's say that we have 49 times 49 over 343. Right, let me zoom in here. Let's say that we have this here. So if you have to do this, there's no rule at this point using exponential rules that will be able to multiply this. So what do we have to do? We have to re-express the bases as prime bases. 49 can be re-expressed as 7 squared. Remember, I am not changing the question, I am re-expressing it. 49 can be 7 squared again, and 343 will be 7 cubed. Right, so it'll be 7 cubed. Again, see here, the quotient rule, but we're also talking about the what? The negative exponents rule, because we have a bigger exponent in the denominator. So what do? We say it's 7 squared multiplied by, and here we subtract the big exponent from the small exponent and we put the base in the position of the big exponent. So it'll be 1 over 7 because it'll be 3 minus 2. And therefore we have 7 squared over 7. Now we're using the quotient rule. And the quotient rule is whenever dividing terms with the same base, subtract the indices. So 2 minus 1 is 1. And that's how we get 7. Very straightforward idea. You just need to remember whenever you're working with exponential expressions, right? You know what an expression is. Whenever working with exponential expression, bring the numerical bases down to prime bases. If you have variables, it's straightforward. You're just following all of the exponential rules because all of that were given in variable form. But if you're given the numbers, the number part is what we have to do. Exactly as I said before, you cannot. How can you break down a variable? There's only one way to break down a variable. I've discussed that in detail with the LCM video. But there's two ways that you can break down a number. But the best way to do it is break it down in terms of only prime numbers. Okay? So, if you have 25 times 125 squared, to multiply this number out without the use of a calculator is going to be incredibly hard. So 25 can be re-represented as 5 squared. Multiplied by 125 is 5 cubed. But we have to include that 2 there, isn't it? Right. So now we have 5 squared multiplied by 5. Whenever you're raising a power to another power, multiply the powers. So it'll be 5. 3 times 2 is 6. Whenever multiplying powers with the same base, add the indices. It'll be 5 to the power 8. And that's how we solve the problem. Very straightforward. Right. So this is basically this part of the linking it to the previous topics, which is linking it to prime and composite numbers. Okay. In the next part, we will link it to orders of operations and see exactly where. Okay, so now, if you have to link this entire topic to orders of operations, very straightforward. I've already discussed this in the algebraic expressions video, where I said that we treat the radical sign as a what? As a grouping symbol, as a bracket. So basically, we think of this as a big bracket. So if I have 2 squared, okay, so let's say that we have the square root of 2 squared plus 12. Then you have to treat the radical sign as a grouping symbol. So you have this big bracket here. Solve what's within the brackets first. So this will break down to 2 squared is 4. 4 plus 12 is 16. And the square root of 16 is 4. Straightforward idea. Right? Just treat the radical sign as a bracket. Solve what's within the brackets first before you start working what's outside the bracket. So if I had a 3 here, and if I had a plus 4, then it will be same thing, same idea. 3 into solve what's within the bracket, 16 plus 4. Then what's the next rule? Work with multiplication. 3 times the square root of 16 is 3 times 4, which is 12 plus 4, which is 16. Very straightforward idea. I just needed to bring this back to your attention so you understand how it links to exponents. And if you had 2 squared plus 4 times 2, then you work with the exponents first. Exponents is 4 plus. Then you work with the multiplication. Remember, BODMAS. Right, work with the exponents first. We've done that. Now work with the multiplication. 4 times 2 is 8. Then work with the addition or subtraction. 8 plus 4 is 12. Right? That's how we get that answer. So that's basically how in this video, we basically linked it to the prime and composite numbers and orders of operations. Now, the next video is going to be very interesting because now I'm going to make another conclusion about why we use prime and composite numbers, and you're going to see the beauty of the section, right? And I'm going to actually introduce a grade 12 question from a grade 12 department paper in this video so that you'll be able to see exactly what I've been saying all along. Right? Like I said, maths from here is going to be very, very interesting. Okay.